Hello guys, welcome once more to another video in our YouTube channel. So in this video we look at June 2020 further maths paper 3 question 4 part 2. So it's from rotational dynamics, and the first part of the question where we are to determine the moment of inertia of the composite body about the given axis. That first part has already been solved, and I'm going to indicate that in a comment section as well as in the description of this video, so that those of you who haven't yet watched the solution of the first part, you just rush to watch the solution of the first part before coming to this video. Or anyways, even without watching the solution to the first part, we can also watch the solution to this video, because basically we are going to be using just the moments of inertia that we obtained in the first part to solve the preceding questions. For those of you who want to prepare for competitive entrance examinations after your advanced level, I bring good news to you. The MAFA organization is in partnership with the most influential group that prepares Anglophone students, which is MIA, Model Initiative of Africa. So centers are all over Cameroon, in Yaoundé, in Douala, in the northwest, in the west, and in the southwest region. In Yaoundé we have almost 7 centers. In Douala we have centers in Bonaberi, in Daedo, in Bonamusadi, in Yala, and in the northwest the centers are clearly written to you. In the west region we have centers in Bafoussam, in Buda, and in Chang, while in the southwest region we have centers in Boya, in Limbe, in Siko, and in Kumba. So for those of you who are interested in preparing for engineering or medicine concourse or teaching concourse after your advanced level, you can get to me directly on WhatsApp so that I register you for the classes and give you more information about those classes. Classes are going to begin on the 12th of June. The GC will be done on the 11th of June. So classes begin effectively on the 12th of June. So make sure you get to me directly so that I give you more information about the centers and how the classes are going to go on, and the modalities, that's the fees you have to pay for the respective classes. And automatically once you get to me and I give you this information, so I will add you to the MAFA online preparation for concours, so that when you're preparing physically at MIA, the MAFA organization will be helping you online, doing tutorial videos like this specifically just for you, not uploaded on YouTube, but those videos are going to be uploaded on our website, and only students that are part of our group will have access to those videos. So guys, let's get started. Right, so let's analyze the equation together. The first part: the object is slightly displaced through small angles theta from its equilibrium position to swing below Q after time t. So this is its equilibrium position, right? And it is displaced through small angles from its equilibrium position to swing below below Q. After time t, we have to show that I d squared theta by dt squared is negative 3 mga sine theta. Then we find the expression for the period of small oscillations of the object about the axis L. Then we show further that if the mass of the rectangular lamina and the mass of the rod are equal, then the component of the force that is perpendicular to the rod exerted by the axis of rotation is 8 on 3 mg sine theta. So let's begin with the first part, showing that I theta dot dot is equal to negative 3 mga sine theta. So first of all, we have to draw the new position of the composite body. So this is its equilibrium position, that is my axis. Now in its new position, it is actually displaced so that it oscillates through small angles from its equilibrium position, all right, and it is swinging below Q. So basically it's going to be giving a horizontal push. So it's going to be giving a horizontal push, all right. And when it is giving that horizontal push, initially this G here is the center of mass of the body. The center of mass of the composite body will lie along the line that is passing through the center of the rod and the center of the lamina. So it's going to lie along this line. So the center of mass of the weight is going to be concentrated at the center of mass. So the mass will be the mass of the rod plus the mass of the rectangular lamina. So I can just call it So the weight is going to be the mass of the rod plus the mass of the rectangular lamina times g. So I just call that the mass of the system. So this is what happens initially. Now when it is after a certain time t, this is what is happening. We have that it is displaced so that it moves through, it is displaced through small angles from its equilibrium position, so that it makes angles of theta. So that's the angle of theta made between the line that passes through the center of mass of the body and the axis L. All right, so in this very position we have that the center of mass of the body is at this point, so the weight is concentrated still at that point, but now this weight is at an angle with this horizontal line, with this inclined line here, and that angle is also theta. Okay, so the weight will have two components. It's going to have a component that is perpendicular and a component that is parallel. So the perpendicular component will be mg sine theta after resolving, and the parallel component will be mg cos theta. Now we need to show that I d squared theta by dt squared is equal to negative 3 mga sine theta. Anyways, still in this diagram we can also indicate the reaction force at the reaction force that is exerted by the axis, exerted by the rod on the axis of rotation. So that force will have two components as well. It's going to have a component that is perpendicular to the plane and a component that is parallel. So the component perpendicular is a transverse component, and the component that is parallel is a radial component. So this was just describing what happens after a certain time t. So it is moving in this direction. All right, this is giving a horizontal push, and this is the direction of theta increasing. The angle is increasing in this direction. So this is omega, the angular velocity. Okay, so to prove this, we can use two laws. Either we use the principle of conservation of mechanical energy, or we use the Newton's law of rotation. Now, for conveniences, I am going to use the principle of conservation of mechanical energy, so that at least you learn something from there. Okay, because if we use the Newton's law of rotation in two lines, we are done. That's it. In two lines we are done with the proof. Maximum two lines you are done with the proof. So I prefer to analyze the equation, because the Newton's law of rotation is derived from the law of conservation of mechanical energy. All right, so let's go through the law of conservation of mechanical energy. Then at the end of the day, you're going to see the Newton's law of rotation coming out clearly, so that in other questions, to save time, you could use the Newton's law of rotation. So the principle of conservation of mechanical energy says that the initial mechanical energy of a system is equal to the final mechanical energy. So we are going to find the initial and the final, and then we equate, and then we do something to get this proof. So the initial mechanical energy is a sum of the initial kinetic and the initial potential energies. Now initial kinetic energy is 0, because kinetic energy is half times I times omega squared. Omega initially is 0 because the angle made was 0, and when we differentiate, remember omega is theta dot, when we differentiate that we get 0. In fact, initially it was not rotating. Omega is the angular velocity, so the kinetic energy initial is 0. Now what is potential energy initial? It is the mass of the system times g times h initial. Now what is h initial? H initial is a distance from the center of mass of the system to the line of zero potential energy. This horizontal line here is what we call the line of zero potential energy. All right, so the h initial here is the distance, is a displacement, the displacement from the center of mass of the body to the line of zero potential energy. This displacement could be negative or positive. Now since it is below the line of zero potential energy, it is going to be negative. All right, now in the initial state, you realize that displacement is just the distance from the center of mass of the body to O, so we can call it OG. But since it is below, then we attribute a negative sign to it. So we have negative the mass of the system G times OG. Now let us find OG before we proceed. So how do I find OG? OG is a distance that is separating the distance from the center of mass of the system to my axis of rotation L. Okay, so how do I find that distance? We need to apply the principle of conservation of moments. That is, the moment of every body in the whole system is equal to the moment of the whole system. So we need to sum the moments of the individual bodies in the system and equate to the moments of the system. Now, there are two bodies. We have the rod and then we have the rectangular lamina. So what will be the moment of the rod? It's going to be the mass of the rod times the distance separating the rod and the axis. But you realize that this axis was actually passing through the center of the rod. Alright, so and the weight of the rod is acting at that point. So there is no distance that is separating the weight of the rod and that axis. So the moments of the rod about that axis will be 0. Okay, so it therefore means that we have the mass of the rod is capital M. Now, so the weight of the rod will be capital M times G. The distance, the perpendicular distance separating the axis and the weight of the rod is 0 because the axis was passing through the center of the rod, and the center of the rod is where the weight is acting, so there is no distance separating. Now let's go to the rectangular lamina. For the rectangular lamina, its own center is actually at its center, okay, and if its center is at its center, then the weight is going to be acting at that point. Now the distance that is separating the axis of rotation and the center of the rectangular lamina is just basically 3a. Why is it 3a? I think if you watch the first video, you're going to understand this clearly. So I'm just going to draw and indicate the length so that you see why it is 3a. So we have the rod, for example, here. Then we have a rectangular lamina. My drawing is not too smooth, so just follow up. Now the rectangular lamina, the center is here, okay. It is different from this center. It's different from the center of mass of the whole body. The center of mass of the whole body is at G, but the center of mass of the rectangular lamina is at this point that I've indicated. Now the axis, this is the axis, all right, and the axis was passing through the center of the rod, and the length of the rod was 3a. So the length of the rod is 3a. It therefore means that this distance here is 3a over 2. All right, this distance is 3a over 2. Now the width of my rectangular lamina was also 3a, okay, and since the width is 3a, it therefore means that the distance from the center to any side is half of, so here is going to be 3a over 2, 3a over 2, and this is also 3a over 2. So you clearly see that the distance between the center of mass, the distance between the center of mass of my rectangular lamina and my axis, the perpendicular distance, is basically 3a over 2 plus 3a over 2, which will give us 3a. That is why we have mg times 3a. Okay, so that's just what I had to explain. Now we need to equate it to the moment of the whole system, which is basically the mass of the whole system times G times the distance from the center of mass of the whole system to the axis, which is OG. Now from here, you realize that we can just find OG. Okay, so OG will just we have to divide all through by G. Then we are going to have OG to be 3ma divided by ms. But what is ms? Is the mass of the rod plus the mass of the rectangular lamina. So the distance from the center of mass of the whole system to the axis of rotation is 3ma divided by capital M plus small m. Okay, so from here you can clearly realize that the mass of the system times the center of mass times the distance from the center of mass of the system to the axis of rotation will just be equal to 3ma, right? I think from here it is clear. So I just have to note it because you are going to use it in many instances. Okay, so from here you realize that we just have to replace OG with we just replace, in fact you see that this formula here has ms and OG. So if I multiply ms and OG, it just gives me 3ma. Okay, so we are going to have here negative 3mag. So this is what I'm saying. We have ms combining with OG to give us 3ma, but now there is a G and there is a negative sign, so everything there gives us negative 3mag. So that is the initial mechanical energy of the system. negative 3 mga. Now we need to find the final mechanical energy of the system, then we apply our principle of conservation of mechanical energy. So the final mechanical energy still we sum the final kinetic and the final potential. What is the final kinetic energy? Basically, kinetic energy is defined by half times the moment of inertia times omega squared, that is theta dot squared, that is the kinetic energy. So initially this theta dot is 0 because theta was not varying, right? So theta dot is 0. Theta was a constant and the angle was 0, but this time around this theta is varying. All right, so the kinetic energy is defined by this half times moment of inertia times theta dot squared. Now we need to add it to the final potential energy, which is the weight times the final h, that is h final. Now what is h final? Let us find h final. So how do I find h final? So h final is a distance. Remember we said that h was a displacement from the center of mass of the body to the line of zero potential energy. So in this case, that displacement, we can call it b. All right, so it's basically in this new position, the displacement from the center of mass to the line of zero potential energy is b. Now how do I find it? I need to relate this b here with my angle theta. So I can also call this other portion also b. All right, so the adjacent, if I try to complete the right angle triangle here, if I try to do a completion of this right angle triangle, okay, then the adjacent of that right angle triangle is just basically my b, or my h final, what I am looking for. Okay, so we can basically use cos theta. If I take the cosine of this angle, I will get the adjacent, and the adjacent is b, then I will divide by the hypotenuse. The hypotenuse is og, the distance from the axis, to g. Okay, so cos theta being equal to b over og, it therefore means that our b is og cos theta. Now since it is our h final, it will be negative b because it is below the line of zero potential energy, since it is displacement. So from here we are going to have attached a negative sign. Our msg remains, hf is og cos theta. Now we just have to simplify. We have to replace our ms and og with 3ma. That is why I had to so this ms and this og again will give us 3ma. all right, then the g is there and then cos theta is there. So all we now need to do is we have to simplify. Okay, so if I apply the principle of conservation of mechanical energy, I'm going to have that negative 3 mag will be equal to half times I theta dot squared minus 3 mag cos theta. So I'm going to differentiate both sides with respect to time. All right. Okay, now how do I differentiate the left hand side? In fact, when you differentiate the left hand side, since it is not with respect to time, it therefore means that it is a constant and it is going to give you 0. The derivative is going to give you 0. Now how do I differentiate theta dot squared? So basically, if I differentiate theta dot squared, I will drop the power, which is 2. I will differentiate theta dot, I will have theta dot dot, then I will multiply it with a theta dot to the power 2 minus 1. That is just the power rule. If you want to differentiate x squared, you are going to have 2x dx on dx. Okay, and dx on dx is 1. That's why we just have 2x. If you want to differentiate y squared, you are going to have 2y dy by dx. That is differentiated with respect to y. So if I want to differentiate theta dot squared, I will have 2 theta dot then I differentiate the theta dot again to give me what? Theta dot dot. Now if I want to differentiate a function that is not in terms of time with respect to time, this function on this portion here, this function is in terms of theta. So how do I differentiate it with respect to time? I use a chain rule, which says that if I want to differentiate a quantity which is not in terms of time with respect to time, I'll need to do du by d theta because it is in terms of theta. Then I multiply it with d theta by dt. The d thetas can still cancel and we arrive back at du by d theta. But knowing fully well that we arrive back at du by dt, but knowing fully well that d theta by dt is theta dot. All right, so when we differentiate this equation above here, once I replace theta dot square, the derivative, with 2 theta dot dot, the 2 will cancel with the 2 in the denominator, and I is constant. So we are on the left hand side, we get 0, like we said, we are differentiating a constant. Now the first term here, we need to have I theta dot dot. Now if I want to differentiate negative 3 mga cos theta, negative 3 mga is a constant, so I just need to differentiate cos theta. Now if I differentiate cos theta, I get negative sin theta. So the two negative signs now become positive, and then you need to attach theta dot because of the chain rule principle that we have had here. So if I divide all through by theta dot, okay, that is my theta dot, I divide by theta dot cancels, then I subtract this quantity on both sides, then my proof is going to be out. I'm going to have I theta dot to be equal to negative 3 mga sin theta. So that is it. Okay, now the second part of the equation, we are asked to find the expression for the period of small oscillations of the object about the axis of rotation L. So period is 2 pi over omega, standard formula, because it's going to be kind of performing simple harmonic motion. And we have to know that since the displacement was through small angles, then sin theta will be approximately equal to theta for small angles, which therefore means that since we have I theta dot to be equal to this, I just need to replace sin theta with theta. Replacing that, we get this. Now I'm going to divide both sides by the moments of inertia, so that I get theta dot equal to negative 3 mga over I times theta. Now if I compare with the equation of simple harmonic motion of a rotating body, that is theta dot equal to minus omega squared times theta, you realize that our angular velocity squared will be equal to 3 mga divided by I, which means that now from the very first part of the equation in part 1, when I solved, this was a moment of inertia. All right, we proved this already, so I just have to replace. Now the 3 in the denominator will cancel with the 3 in the numerator, so this 3 is going to cancel, and the 4 in the denominator will go to the numerator, okay, and then the a in the numerator will cancel with one of the a's in the denominator. So simplifying, what are we going to have? We are going to have something like 4 mg divided by 17m plus capital M times a. So that is omega squared. Now what's going to be omega? This positive square root, all right, the positive square root of this quantity. And since my period is 2 pi over omega, if I take 2 pi over this quantity, I am going to have exactly this, because the square root of 4 mg is the same as the square root of 4 times the square root of mg. The square root of 4 is 2. So it's going to cancel with these 2, and we are just going to be left with pi. And since we are dividing, then we are going to we need to interchange, we need to switch the numerator and the denominator. Okay, so just try to work this out on your own, and you're going to have exactly what I have here. So this is a period, this is the expression of the period of small oscillations of the object about the axis of rotation. Okay, now we are moving on to the last part of the equation. Show that the force that is perpendicular to the component of the force perpendicular to the rod exerted by the axis of rotation is this. So that perpendicular component of the reaction is just the transverse component, which is ROT. So we need to show that when at the instant when the mass of the rod is equal to the mass of the lamina, the rectangular lamina, then that perpendicular component of the force is given by this. So first of all, like we said, that it is displaced from its equilibrium position and it oscillates through small angles. So this is basically my direction of motion. Okay, so this is my direction of motion. First of all, this proof is incorrect. yes, we had to talk about this for a couple number of days, and we came to the conclusion that this proof is not really correct, and I'm going to show you why it is not correct, and I'm going to show you also what the equation kind of, let me say, what to do to have the proof that is actually the wrong methodology. Okay, because I try to visualize how it is possible for you to use that wrong methodology and actually have the proof. Anyways, we go via the correct knowledge. Okay, so we need to basically apply Newton's second law of motion along this axis. That's what we have to do. We have to apply Newton's second law of motion along this axis. Okay, so if you apply Newton's second law of motion along that axis, you realize that since the body is moving in this direction, okay, that is the direction of theta increasing, and if that is the direction of theta increasing, then the transverse component of the acceleration is in that direction. Okay, so Newton's second law of motion says that the resultant force in any given direction is a mass times the acceleration in that direction. So the resultant force in this direction is just the force taking it in the direction minus the force that is trying to resist the motion, that's the resultant force, now equal to m times the transverse acceleration, because in this direction we are in the transverse direction, we are perpendicular to the motion. So we have that if we apply the Newton's second law of motion, then we have ROT, this force, minus this resistive force, which is the perpendicular component of the weight, which is msg sine theta, to be equal to the mass of the system times the acceleration in that direction. Now, what is transverse acceleration? It is 2 r dot theta dot plus r theta dot dot. Now, what is r dot? What is r first of all? R is basically OG, alright? That is the distance from the axis of rotation to the center of mass of the system. And this distance is constant. And since the distance is constant, it means that r dot will give you 0 because you are differentiating a constant. So everything here becomes 0 plus my r here is OG. Then we need to multiply with theta dot dot. But what is OG? Anyways, we are going to have OG times theta dot dot. So from here, we just have to replace the transverse component of the acceleration with OG times theta dot dot. Now we need to add MSG sine theta on both sides. Then we have this. Now what happens is that capital M is equal to small m, so the mass of the system will be 2 times small m. Okay, because the mass of the system clearly is capital M plus small m. So if capital M is equal to small m, then we have small m plus small m to be 2m. So my transverse component will be 2mg sine theta. Then what is mgs OG? mgs OG is just equal to 3ma. Here is it. That's why I had to keep this from the beginning till now. So mgs OG is 3ma. Now we need to multiply with theta dot. Okay, so the next thing is to do is that let us try to look for theta dot, or 3ma theta dot. So let's just try to look for if we can find this entire quantity. So we go back to the proof we had initially, and then we just replace the moment of initial I with the value of the moment of initial. Now we multiply it with theta dot, then we equate it to negative 3mga sine theta. Now you realize that from here, if I divide all through by a squared over a will give me a. Alright, now I'm going to replace capital M with small m, so 17m plus m gives me 18m. Now what is going to be 3ma theta dot dot? So I'm going to keep this, I'm going to keep this, and I'm going to keep these two guys on the left hand side. Once I keep them, it means I'm just going to multiply both sides by 4, then I divide by 18. So doing that, we are going to have that 3ma theta dot dot will be equal to 4 times negative 3 is negative 12 mga sine theta, then divided by 18. That is what we have. So all we need now to do is we just have to replace 3ma theta dot dot with what we have had. So we have to replace it and then we simplify. Okay, so if you have actually watched till the end of this video, then it was not really easy. Congratulations, this is already 29 minutes 39 seconds. It's not easy to be here till the end, so congratulations to you. So all we need to do is we have to replace, we have to do a substitution, and when we do that, we just have to simplify. All right, so doing that substitution, we are going to have 2 mg sine theta. Now 12 on 18 is 2 on 3, because 6 will go into 12 2 times and to 18 3 times, so we have minus 2/3 mg sine theta. Now mg sine theta is common, so we are going to have 2 minus 2/3, and 2 minus 2/3 is 4/3. So it means that my answer is 4/3 mg sine theta and not 8/3 mg sine theta. Now what will I do to actually have 8/3 mg sine theta? Though it is not really correct according to me, but doing it, you are going to have the answer. Okay, so if we instead consider that the motion is in this direction, okay, then we are going to have 8/3 mg sine theta, because what will change is just the fact that instead of taking ROT minus mg sine theta, we are rather going to be taking mg sine theta minus ROT, and when you do that, you're going to have the answer. But left on to me, according to the way the diagram was given to us and it was displaced, I don't think the body can oscillate in that direction. That is, I don't think that the angular displacement can be increasing in that direction. Angular displacement is the angle of rotation. All right, so basically it's going to be in this direction, so the change in angular displacement will also be in that direction. So basically I think that is what I had for you guys. If you're new to the channel, don't forget to like the videos, share the video with your friends, very important. This question was very technical. If you have not watched part one, we're just applying the theorems in moments of inertia to get the moments of inertia of the whole body about the given axis. If you have not watched part one, make sure you check the comment section. I'll pin the comment of the video of part one, so that you just go and you watch it. Then maybe after watching this one, you go and then you watch part one to understand theorems in moments of inertia. There are so many videos in this channel that I've produced on this topic, so you can also check the description of this video. You'll see the list of videos that I have produced in this topic. Okay guys, thank you once more for subscribing. You see, right now we are around 4,050 subscribers, and this is all because of you. So make sure you continue sharing so that we reach out to so many people and we help them academically. Thank you guys for watching, and make sure you get to me for prep classes. See you in the next video.